Welcome back, my statics friends. Up to this point, we've spent a lot of time studying how to create resultants and find components of forces and vectors. But now we're going to start turning our attention to how do we apply that to objects in the everyday world. And the first step and most important step is the creation of free body diagrams. So I'm going to show you a W.I.S.E methodology for doing just that. So without further ado, let's get started. So free body diagrams are pictures that include a lot of different information that you need in order to be able to apply equations of equilibrium and statics principles to these. And so the methodology that we use follows an acronym known as W.I.S E, W-I-S-E, for creating those. And so I want to kind of walk you through what each of the letters stands for as kind of a reminder, because it is indeed a wise idea to draw free body diagrams before solving any statics problem. So we're going to start off with W. That is our self-weight, okay, which is the gravitational effects of the mass. So it's m times g. You've seen those. And usually in most statics problems, especially in this series and in this class, we often neglect this because it's such a smaller value compared to some of the applied forces. Now, that may not be the wisest thing to do. We probably should put it on there. But again, in this class, we neglect it often. One of the tips that you know when you have weight dealing with it, they may not talk about weight as a force, but they may, and especially in SI units, you may see some note about the mass, being expressed as kilograms. Okay, if you ever see a kilogram or a gram value in a statics problem, chances are it's a self-weight that they're dealing with, and you've got to be able to convert that to a force. So if you remember, weight is going to be equal to mass times the gravitational constant. For SI, that's going to be 9.81 meters per second squared. Okay, in the US units, okay, usually this is expressed straight away as pounds. Okay, and if that's the case, then there's no conversion needed. So there is a little bit of a difference depending on whether you're working in SI or US units. So that's the first one. Okay, the I in WISE is for internal forces that are revealed when we cut an object, in order to isolate things or to study what's happening inside the object. And its requirement is that when you cut it, if the object is in equilibrium before, then the object afterwards also has to be in equilibrium. Okay, so I've got a simple example here to show, I've just got a tension member. There's a tension force here and a tension force here. And clearly this guy is balanced, assuming that the line of action of all of these forces, each force is balanced on that thing. But if I go through and I cut this object apart, okay, and then I draw the piece above the cut and the piece below the cut, this is the picture that I get. And now if you look at just this piece, what you can say is, well, clearly this is not in equilibrium. This object is going to want to move up and to the right. So there has to have been something here when it was connected that we call as an internal force. So I would label that as T internal. Okay, and so now if T internal equals T, this object is indeed in equilibrium, and it turns out that is indeed the internal force of this member. Okay, now go look at the lower part of it. And what you'll notice is, well, again, the T applied on the outside, it's the same T that was here. This object wants to move down to the right. So there must have been something here that is holding this piece in place. And so if you notice what's happening is this region right here, could be, one atom, one micro element of this rope is also being balanced by forces that are acting on it. Okay, and so this, I have a T internal down and to the right and one up and to the left. These guys would cancel. The net effect on this particle then would be also zero, which is also in equilibrium. So these are the internal forces that we're talking about, and there are lots of different ways that we're going to kind of talk about these. And in fact, a lot of what we do from here on is all about the assumptions made about the internal forces. All right, so this is what we call as an axial member. In more complex problems, you can get additional forces and even moments that show up as internal effects as we start to look at it. And we'll talk about those more as we get into some of the applied problems here later in the series. But for now, this is the idea of what an internal force is. You've got to have equilibrium at all parts, even after you cut them, to look at it. Okay? All right, the next one is going to be our support reactions. Okay, and these are restraints to the outside world. And I'll show you some examples here in just a second. Or restraints of motion, if you will. Okay, an object wants to move, and if we stop it from moving, you have to apply a force or a moment in order to stop that motion. Okay, and so these will be very important, especially in equilibrium problems. So that's our S. And then finally, the E in WISE is actually the external loads. Okay, these are the forces and the moments that are applied to an object and their locations that we typically know these in any statics problem. So that's the WISE acronym. So let's dive in and talk a little bit more in detail about some of these different ideas. Okay, so the first one we want to look at is we want to look at the support types. Okay, so in two-dimensional problems, we're going to look at basically three classic support conditions. Okay, the first one is a roller, and basically what's happening is that there is a support that is here, okay, and it's free to move left and to the right. It can move, basically like a pair of roller skates or a wheel or something, and this object is able to roll back and forth. Okay, it can't go up or down because the ground is holding it in place. So that's the restraint to the motion that we're talking about. It's free to do whatever it wants left and right. There's no force in that direction. But this wants to move down, assuming that there's gravity acting on the beam. So in order to hold that in its place at that location, this boundary condition, if you will, we have to apply a force F perpendicular to the surface. Okay, now one of the things that we can kind of take note of here, get another piece of paper here, is that force direction is always perpendicular to the support on which it's rolling. So if I have, say a round object that is here, a roller that's on a vertical rolling surface on this, and here's my support, then the reaction that we have would be just a single force here. Okay, and it's free because it's free again. It's free to move up and down, whatever it wants to do, but it's being restrained from moving left to right. All right. Now, this roller, got to be very careful that it's pushing on the wall, but it's also being restrained if I try to pull it away from the wall. So a lot of times, a true roller is actually some sort of assembly that has some sort of slot in it, and then there's a pin, and so it can drift up and down. But if I pull this way, it hits this part of the bracket, and if it pulls the other direction, it hits the other. It can't pull away. It's locked in that position, but it is free to slide up and down. That's another type of roller that you'll see, kind of a slotted assembly like that. All right, the other one that we want to look at then is what happens if we have a ramp and a roller is happening here. So here's my roller, and now let's just say that the member is horizontal. It could be vertical, it could be anything, right? That's a horrible circle. And let's clean that up a little bit. Okay, a little better. Okay, so the reaction that shows up on this, again, the definition is that this is 90 degrees. And so this one would be this direction, F, and if this is some angle that we can say is theta, that's 90 degrees off of that theta. Okay, so if we kind of look at the components of this, if I drop a vertical line down here, and this is my line of action of my force, then this is also theta. Okay, and so that would be the way that we kind of look at it. But it is still a single force because it's free to move this way. Okay, now, as we declare these forces, we don't always write them in X and Y notation, so this is a common trick to be able to handle this. Remember, just because I have this force, I can turn that guy into, an Fy component, and here's an Fx component on that. Okay, and if we look at this, then again, this is my angle theta. It's kind of drew it differently, but if that's theta, this is the opposite interior angles theorem because that's 90 degrees. But I can always take this force that's a single object and replace it with these two guys. So you can write this as a picture that looks like an Fy and an Fx, but in this case, my Fy is going to be F times the cosine of theta, and my Fx is going to be F times the sine of theta as we start to look at that. And notice that they both use the same F, they both use the same angle. So this is what we call a coupled pair of forces, that both of these values are related to both F and theta. Okay, so they're coupled together, as opposed to the next one I'm going to show you, in which that's not always the case. All right, so that's the situation that we want to look at for a roller. All right, so we'll put a note of roller on this guy. Okay, all right, so back to our picture. The next one is what we call as a hinge or a pin support. Okay, and so if we think about the behavior that's happening on the roller, it was also free to rotate. Okay, nothing restraining it. A pin then is going to be a system in which there's a locking mechanism on this that it's free to rotate, but it can't move left and it can't move right. And so when that happens, we have Fx and Fy again, but now they're independent. They're not coupled together on this because there are indeed two forces that are happening on this. Okay, but it is still free to rotate, meaning that there is no moment. Okay, moments are related to rotation and forces are related to translation. And so we're looking at that as our basic picture. Now, for the pin condition, typically we draw them as X and Y components. Okay, but again, I don't necessarily have to do that, and there will be some tricks that we can apply to this. That, okay, here's my Fy, here's my Fx. Well, sometimes it's more convenient, say I have an object that is, pinned here. And again, physics professors and static professors always like to do things on inclines just to make sure that you understand the direction. As long as I have two forces that are not in the same direction, call that as F1, call this as F2, this is still a valid free body diagram for a pin connection, F1 and F2. Okay, I could also draw this one, and if for whatever reason, maybe all my forces are at some angle, I could draw it this way. Okay, but I can write them as pairs. So here's an FA, here's an FB. In fact, they don't even have to be 90 degrees to each other. I could do this, let's call this, I don't know, for lack of a better word, this FM and Fn. So long as the resultant of this, because remember, I can take two forces and I can always turn it into an F force using our parallelogram law or using our components rules for vectors. Okay, as long as this F is the same for all of these pairs, the free body diagram will work. And so there are reasons to do this. Most often it's the Cartesian system, X horizontal, Y vertical, and sometimes this one pops up. But occasionally, especially in machine design and stuff where you have slots and cams and bearings and things happening, that sometimes it's more convenient to go to a non-Cartesian system. You just got to kind of try and find one that works best for you. But it is two forces that are unrelated to each other that form a resultant force that is the same for all the pictures. And then in that case, the picture doesn't matter. All right. The last one that we have is then the fixed support. Okay, and so if you notice, we're kind of adding degrees of restraint to all of these. This guy was free to move left and right, but couldn't move up and down. This guy can't move at all, but he could rotate, as could this one. Now we're going to restrain the rotation as well. And so a fixed support has neither translation nor rotation on it. And so when we draw a free body diagram for a fixed support, it's going to have a vertical force, a horizontal. And again, this is that pairing that we just talked about. As long as I have two of them, not in the same direction, it's valid, as long as I can find their values. And then we also have an applied moment that provides the restraint to the rotation. Okay, and so these become our basic pictures. Now, there are some other three-dimensional ones that we can look at. Okay, things like, maybe we have a three-dimensional rod that comes down and is locked in at a point like this. This is what we call as maybe a ball and socket. Okay, or a 3D pen on this. And so this one is basically, it would be, a system where it's held in place at a point, but it can rotate however it wants. But it only has, maybe this is my Fy, here's my Fx, and then maybe in this direction you would have an Fz. And again, we're looking at a three-dimensional problem. There's my X, there's my Y, or sorry, that's my Z, and then my Y positive would be up. That would be a ball and socket. Okay, the idea here is no moments. That's another very, very common one. You can also have, collar assemblies, which are kind of interesting. So, okay, in which case, if this is the line of the shaft, you would have some object that is basically, you have a shaft that's here, okay, and then you have some other. So imagine, I take it and I grab it this way. My hand can move up and down on the shaft, but it can't pull off. So if you think about it, it's free to move along the shaft. Okay, but if you think about, again, if we're looking at this pencil, what kind of things can it do? It can move this way. Okay, it can rotate this way. So there's no restraint or no moment about that axis. Okay, but I can't pull up and I can't turn any other direction. So this type of system would have, say, if I define my coordinate system, I might have, an RY. If this is an x-axis, kind of keep our convention the same, our x-axis. Okay, in addition, at that location, there could be some sort of restraint or some sort of moment about the y where this thing cannot twist about a vertical axis this way. Y positive. Okay, so you would have a force and a moment. Again, I'm drawing my moments as double-headed arrows. If you don't remember what this means, go back and look at our moment videos and we'll kind of explain what that is. This is a moment that wraps around the y-axis. Okay, and then the other one that you would have might be, in this case, if this is my z-axis, then you might have an RZ, and then likewise, you can't rotate around that axis either. You would have an MZ. Okay, and so depending on the axis of this assembly, normally, a fully rigid connection would have all 6 of them. A full fix on this, and I know we're getting a little bit, that if that's, a fixed support, you would have this is RY, here's MY. Oops, get that up there a little bit so you guys can see. Okay, and again, we're looking at our y-axis this way, and then we would have an RX and a moment about X. There's my moment at X. Okay, and then likewise coming this way. Okay, there's my RZ, and then this one would have an NZ that looks like that. Okay, and again, we're assuming Z positive this way, Y positive up, and then X positive that way. This is a full fix. All right, so the fully fixed scenario has 6 effects, 3 forces and 3 moments. The collar is basically a release of one of the directions. Okay, and so you would draw your picture. If your shaft were up and down, these directions would change, but those are the cases that we're looking at for some 3-dimensionals. And these are probably the most common 3-dimensionals support reactions that you'll find. All right, okay, so if we go through and we look at that, let's see. What else we got? Kind of back on our topic, we've talked about the external forces. Those were the applied loads. They're usually known. The internal forces, then, we've talked about as being revealed, required for equilibrium, and then the self-weight, we've done that as well. So we've done all those. Okay, so let's take a look and kind of figure out what we can do with this in kind of just a simple free body diagram example. Let's suppose that I have, a cable system that is tied at A, tied at C, has a ring here at B, and from that ring, we're suspending a box or some mass on this. Let's say that the box has a weight of 20 pounds. Okay, the way that we draw this is the first thing we do is we draw a free body diagram of the entire system. Okay, and so if I go through and I do that, we would have at this pin, that's a pin support at A, we would have an AY, and I would have an AX at that location. And again, my picture's a little small. Okay, and then we do this, and here's my ring, and then this guy goes over to this. Okay, and so this letter is C, so we have a CY and a CX happening there. And then coming down, we would then have our box that's hanging here. Okay, and we can kind of go through and do our Y's. So we have W.I.S.E. Okay, the box weight. So the box itself has a weight. So you see that word weight, that's a tip-off. So we would have then the full free body diagram would look something like this, that there is 20 pounds on the box. Okay, my I is an internal. Okay, but in the first free body diagram, we didn't cut anything. I put an isolation box all the way around this outside of this thing. I cut nothing. And the reason we do that is by cutting things, we start revealing extra unknowns, and so we want to kind of look at techniques that will speed us up in our analysis process. Right now, if I look at my free body diagram, so my weight is done, my no internals, S is my support reactions, they were pinned, so I had an AX and an AY and a CX and a CY. Okay, and then E is my external forces, and there are no real external forces. I mean, you could call the 20 pound as an external force if you wanted, but we're treating it as a weight on that box. This is the full free body diagram. Now, if you look, you have three equations to work with: sum of forces X, sum of forces Y, and sum of moments. But I have four unknowns on this. So this is an unsolvable system as it's currently drawn. So that's where we have to go in, and sometimes you get lucky and you can find one or two of them, even if you have, four unknowns. Not always, but sometimes you get lucky. This one you don't. You can't find any of them, even if I knew all the dimensions and the angle. And again, there's an angle theta that's here. Okay, so then we have to start looking at, well, how can I start to cut this apart to find things to work with? All right, and so what we're going to do is we're going to take a look and we're going to cut we're going to start to cut and look at pieces of our puzzle here. Okay, for example, I can draw an isolation box around any part of the structure, and what an isolation box is basically a closed polygon, and I usually draw them as a dotted line, and so maybe I wanted to just look at what's happening in the rope. Okay, and when I do that, here's my rope. Okay, and so now anywhere that my isolation box crosses the object, an internal force is revealed. So at the top of the rope, I would have an FBD. Okay, if I draw another one around the weight of the box, very quickly you can see that I would have whatever that force internal is on the box, and then I would have my 20 pounds there. Okay, and that would be the free body diagram of the isolation box around the weight. Well, this guy, if this is 20, clearly this is 20 also. Okay, and so these two right here end up being the same value. So now I can move up to the rope. So here's a 20 pulling on the rope, and then this goes in and pulls on that, and so there's a 20 on that. I know FBD is the tension in the rope is 20 pounds. And I get that by simply taking this object and doing sum of forces in the Y. That FBD up, and if I assume up is positive, FBD minus 20 better be equal to 0. This is the first check on equilibrium. And if this isn't moving, then I know that's equal to 0. That's how I know the tension is 20 pounds. Okay. We can also go in then and we could draw, say, a free body diagram around the ring. Okay. And part of the deal with statics is learning what to draw and how to draw things. So if I draw an isolation box around B now on there, I've now cut the rope here, I've cut the rope here, and I've cut the rope here. Okay, and so this little piece inside would have a picture that looks like this. Now ropes, when you cut them, are always in tension. Okay, so our cables, if you will. Okay, that there is a tension in this cable that we would call BA, from B pointing at A. Okay, there's a tension in BC from B pointing at C, and then the bottom one from B pointing at D. Here's the FBD force, the one that we just found up here, that this value and this value have to be the same. So we know that this is 20 pounds. Okay, once I have that, then I can go in and I can start to solve for things. But this is how you can start to progress. Okay, so I could do a sum of forces in the X, and here, let's just do that. Okay, so for this picture here, we could write sum of forces X equals 0. We'll do this way positive. And when I do this, the equation that we get would be a positive FBC, okay, minus FBA cosine of theta. And then sum of forces in the Y direction equal to 0, upward positive, would be a positive FBA times the sine of theta. So that's the vertical component of this guy, the piece that's acting in my Y direction, okay, minus FBD, all equal to 0. Okay, that's the first, or what equilibrium is doing for us. It's allowing us to find these internals. Now I know that this guy is 20 pounds, right? So then that means that FBA is going to be 20 pounds divided by the sine of theta. Okay, and so whatever this angle theta is, that's the force in FBA. And there will be some things that we'll have to look at with regard to the sign of him and how they correlate to free body diagrams. But for the most part, that's all there is to it. And then with this, I can go back up here, and this is going to tell me then that FBC is going to be equal to FBA times the sine of theta. And so then I can plug this in over here. Oops, that was not the sine of theta. That is the cosine of theta. Right there. Okay, and so then I can say, well, this was 20 over the sine of theta, and put units on here, 20 pounds times the cosine of theta would be 20 pounds over the tangent of theta. And that would be the value of FBC, or in this case, the tension in that rope right there. So that's how you can start to solve these things, just by knowing how to dissect these things. Once I have those, now I can go up and we can say, well, let's look at support A in this example. Okay, so here was my support reaction. We said in the original picture there was an AY, and here was an AX, and here's my rope. But now we're looking at the other side of the cut. So this would be my force in BA on the rope. It's in tension, so it has to be pulling on my rope segment. Looks something kind of like that. And again, this is the angle theta, right? Well, let's do it again. Sum of forces X equals 0, to the right positive. It's going to tell me that AX, okay, plus FBA times the cosine of theta is all equal to 0. All right, and then sum of forces in the Y equal to 0. This way up is going to be then AY plus FBA times the sine of theta all equal to 0. Okay? And I blew a sign, minus. His component is now, I got a piece acting this way and a piece acting this way. That's a minus right there. All right? And so since I know FBA from up here, I can now solve for AX. And something interesting happens here. AX is going to be equal to a minus FBA cosine of theta on this. Okay, and so if we look at this expression, for positive values of the angle, FBA is going to be a positive value always. So this minus sign, this tells you that AX on your free body diagram is backwards. It's opposite direction. It's not truly in this direction. And that should make sense, right? If I have an X component to the right and AX is to the right, there's no way that can be in equilibrium. So if I'm pulling on this, AX has to be pulling backwards, okay? This is Newton's law, equal and opposite, right? In order to force equilibrium. You know, every force has an equal and opposite reaction. Well, that's the reaction that's happening on it. So this minus sign can be a clue that even though I drew the picture wrong, these minus signs, if you watch them carefully, will tell you if your picture is correct. And we'll take advantage of that in future diagrams, okay? So again, I didn't know what it was doing on this picture, but now I could solve for it and find out, oh, it's really pulling to the left, but I could still do the math and set up the statics equation. All right, and so that's how we can look at that. AY in this case, if we look at it, AY is equal to a positive FBA times the sine of theta. And so this guy is positive for all values of, for all values of theta, because FBA is always positive and theta is always positive. AY is positive, which tells you this AY is in the right direction. And that should make sense, right? The component of FBA is down, so AY better be up to hold it in place. And so that's kind of the idea of where we're going with drawing these free body diagrams and what I can start to do with those. We just got to kind of be careful on how you set up these free body diagrams and work from there. So that's kind of the basics of WISE and what you can do. It's a lot of practice and a lot of experience will show you how to make these cuts and what to look for. You could go do the same thing on support C, draw the same picture, write the same equations. And so you're starting to see a pattern already, and this is really our first example of equilibrium, is that we draw a free body diagram and then I write the equations. And then I draw more free body diagrams after I've cut things and I write more equations. And eventually, hopefully, you can solve for some pieces. All right, now, not all problems work that way, but for a lot of them, you can at least find something to work with. okay, even if you can't find everything. And then in your future classes like mechanics materials and strength of materials, you'll actually come up with techniques to be able to handle it when you can't find everything. What do you do? There's some other tricks that is kind of beyond the scope of this class. But that's the beauty of what statics is, and these Newton's basic laws and principles, and all of that work that we did with vectors and components and resultants in the early chapters all come back to play starting now. Okay, so you can solve a three-dimensional problem the exact same way, except now, you know, what would have happened if instead of doing it with the scalar pieces like I did, I came in and said that there's some RA vector on this, and then I have, you know, this force, this FBA rope here, you know, that is now, I make a unit vector and turn that into a vector itself. Well, what do we know? In order for this to be in equilibrium, the resultant of this system I know is my reaction at A, which is made up of, you know, I could even go so far as to say it's an AY component and an AX component vector. Okay, RA plus FBA, which is going to be an AY vector plus an AX vector plus my vector for FBA. And if this is in equilibrium, all you're going to end up doing is saying that this is equal to a zero vector, 0i, 0j, 0k. And so that's the beauty. All we're doing is we're finding components and resultants, and now we're going to set its limiting value for equilibrium to 0 for the resultant. Now, there is also moment equilibrium where the resultant moment must also be 0, but I'm not going to worry about this because all the forces are acting through the same point that support on this one. But we'll pick that one up here in the coming videos. So I hope that's made sense to you. Remember, it's always wise to draw a free body diagram. I thank one of my former students for coming up with that acronym, but it works. So W.I.S.E, weight, internal, supports, and external, as we start to kind of work on that. So I hope that's made sense. As always, if you've got any questions, leave us some comments down below, and be sure to like and subscribe to the video, and we will see you guys next time. Happy engineering.